Dear students, welcome to yet another online tutorial on principles of communication system. So we are into fourth module, and this is the third video of fourth module. In first two videos, we have discussed about the basics of digitization, the sampling process, mathematical modeling of the sampling process, and also some of the very important prerequisite for you to appreciate the sampling theorem or sampling process, right? So in today's session, we'll be discussing about the ideal sampling and the sampling theorem, or sampling theorem is also known as Nyquist sampling theorem or Nyquist criteria. It tells us basically, right, what should be the sampling interval, or what at what rate the sampling should be done so that the samples can reliably represent the original signal, and from the knowledge of the samples we can reliably reconstruct the original signal. So that's what we are going to see in today's session. So before we go into details of this, we'll just quickly revisit what actually was right, this ideal sampling process, right? So we are considering a finite energy signal. Say this is our finite energy signal, we are representing it as g of t. The signal is to be sampled, right? So we assume the signal is of finite energy, right? And this is defined for all time. So even though I've shown for a small duration of time, right, it's a part of the signal, you can assume, right? So and it is a band limited signal, right? So we'll be discussing about sampling theorem for band limited signal or low pass signal. When I say band limited signal, its maximum frequency content will be w hertz. That is, if I take Fourier transform of this, right, the spectrum will look like this. So this is our g of f. It will have maximum frequency content w, so it will span from minus w to w. So this will be our spectrum. So we are going to sample such a signal, right? So basically, to sample, what we'll be doing is we'll be multiplying the signal with an infinite impulse train, right? So that we'll be getting the sampled version of the signal. So that's what we'll be doing. So we have this g of t. This g of t will be multiplied with an infinite impulse train. So infinite impulse train can be represented as n from minus infinity to infinity del of t minus n ts, where this capital Ts is the sampling interval, and 1 by Ts, that is equal to Fs, will be sampling frequency. So we'll assume the capital Ts is sampling interval, and 1 by Ts, that is equal to Fs, will be sampling frequency or sampling rate, right? Sampling rate, it simply means there will be Fs number of samples in a second, right? That's it. So if you multiply g of t and this impulse train, so impulse train is nothing but what, it's chain of impulses separated ts apart, right? So this is 0, this is ts, this is 2 ts, this is minus ts, minus 2 ts, so on and so forth, right? So this is an ideal impulse train spanning from minus infinity to infinity, right? So if you multiply these two, we'll get g del of t. This is our sample signal, that is nothing but what, g of t into summation n from minus infinity to infinity del of t minus n ts. As this del of t minus n ts, the trains are defined only at time instances n ts, right? I can take this g of t inside the summation, and I can rewrite it as maybe g del of t will be equal to summation n from minus infinity to infinity g of n ts times del of t minus n ts, where g of n ts will be the instantaneous values of the signal g of t at time instance n ts, right? And del of t minus n ts are nothing but these impulses. So we can represent this, right? So if this is the arbitrary signal which we have considered, right, the sampled signal will be something like this, right? It will be, right, right, these impulses weighed by this g of n tss. Then this is our so this will be 0, ts, 2ts minus ts, so on and so forth. So this will be g del of t, right? So this is the sampled signal. This is the sampled signal. Sampled signal. Now, what we need, so mathematically, we can represent a sampled signal like this. Now, what we need to do is we should know what should be this ideal sampling instance, so that these samples can completely represent the original signal, analog signal, right? And also, with the knowledge of these samples, we should be able to reliably reconstruct the original signal. For that, what should be this ts or what should be the fs? That is our, right, that is what we have to find out, right? So the answer to this is actually what sampling theorem, right? So but before for that, actually it would be better if we can represent it in frequency domain, right? So if we can represent it in frequency domain, that will give us more idea. So if I'm directly taking Fourier transform of this, we have discussed it in last class, right? So this g delta of t, its Fourier transform can be what, g del of f, right? This is equal to, and summation n from minus infinity to infinity, it will come as a g of nts. It's a scalar, or it's actually what, constants, right? So those g of nts can be written as such. This del of t minus nts, its Fourier transform will be nothing but e power minus j 2 pi n ts into, say, f, right? This will be the Fourier transform of this. But right, this expression of g delta of f as such actually won't help us to visualize the spectrum, right? In fact, this is the discrete Fourier transform expression, right, of this g del of t, right, or discrete Fourier transform of this uh, impulse trains, right, or discrete signal. So if we want to evaluate this, we should have the knowledge of each and every samples, right? So but it won't help us to visualize what actually is the spectrum. So maybe what we'll do is we have discussed in last class about the spectrum or a Fourier transform of periodic pulse train. With the help of that result, and also with the concept of duality, right, we can find out the Fourier transform of our this g del of t. So maybe I'll just once again I'll write g del of t, right, of which we have to find Fourier transform. It is nothing but what, summation n from minus infinity to infinity g of n t s, right, times del of t minus n t s. This is the signal of which we have to find Fourier transform. So I'm calling it equation number A, right? So now, right, we'll just recollect what we have seen in last class, right? So maybe the sampling process, right? There we have seen, right? So the Fourier transform, if x of t is this entire left hand side, right, it's Fourier transform x of f. So this x of t here is actually what, a periodic signal with the pulse corresponding to one period being g of t, right? Don't confuse with the g of t which we have used here. This is a standard result which we have, right, obtained in last session. Those who watch the video will be able to appreciate this. Otherwise, please do watch this video before you continue watching this. Otherwise, I try to follow. If you find it difficult, you can go back and revisit that video again, right? So if this is x of t, then the x of f will be of this form. So this result is what we are going to use. This is a result from last video, right? So I'll just rewrite this result here again, right? I'll just rewrite the result again. So excuse me 1 second. Right. So what we have is, if x of t is equal to summation m from minus infinity to infinity, say g of t minus mts, right? G of t minus mts. If this was x of t, right, then Fourier transform of this, right? If you take Fourier transform of this, Fourier transform of this, that is x of f, it is equal to, right, f naught, where f naught is nothing but what, 1 by ts, right? Okay, f naught times summation n from minus infinity to, or m from minus infinity to infinity, right? We can, or n from minus infinity, g of m f naught times del of f minus m f naught. So we can write it like this. So this is the Fourier transform of a periodic signal, right? So it's like this. So if you compare the um, time domain expression of g delta of t and right hand side of this much part, you can see those are similar, right? Instead of g of n ts, we do have here g of n f naught. This can be n or m, whatever, it's not a problem, right? Right. So I've just used n and m, right? Please don't have confusion. That's it, right? So this g of nts, it's a constant, right? Or which will be value of instantaneous samples, right? So similarly, we have here g of m of naught, right? And del of t minus nts, instead of t we do have here f, right? And instead of ts we have here f naught, right? Where this ts will be equal to 1 by f naught. So but what we have is one additional f naught is there, but as that is a constant, right, we can easily rearrange it. And right, so then, right, this is x of f. So in this x of f, right, our g delta of t is a function which is like actually what, capital X of t. So in this particular frequency domain expression, if you replace f with t, what we are getting, that will be actually what, our g delta of t. So we can use, right, so we can use duality property, right? So I'm right, why duality, right? If x of t, its Fourier transform is capital X of f, then Fourier transform of capital X of t will be x of minus f, right? It will be x of minus f, right? So that's what the duality theorem. So by applying this duality, we can write the Fourier transform of, right, the Fourier transform of summation n from minus infinity to infinity g of n ts times del of t minus n ts, right, as, right, we can write it will be f naught times summation n from minus infinity to infinity, or m from minus anything would be fine. So m from minus infinity to uh, infinity, right, g of f minus m f naught, or f naught, I'll use fs, right? Fs we have used, it has sampling frequency. This is nothing but what, 1 by ts, right? So this is the Fourier transform, right? This is the Fourier transform. So if you closely inspect this, right, this is actually what, g of f shifted by an amount fs, right, or mfs, right? And this m is running from minus infinity to infinity. So I can we can see it as actually what, the spectrum of g of f replicated at every what, multiples of fs on either on positive and negative side. That will be the spectrum of our g del of t, spectrum of g del of t, that is g del of f, right? That is g del of f. This entire thing is actually what, f of Fourier transform of this will be g del of f, that is equal to this fs times g of f minus ms. So it is of course, right, weighted by the amount fs, that is a constant, that is the sampling rate, and g of f minus mfs. So maybe we can try and visualize this, how it will look like. So we know g of f, right, g of f is a band limited signal, right? It will be spanning from minus w to w, right? And so this is g of f. So g of f minus fs will be actually what, the shifted right by an amount fs. G of f plus fs will be this shifted left by an amount fs. If it is g of f plus mfs, it will be shifted left by an amount mfs. So this um, spectrum, right? This spectrum, that is we can represent the spectrum as, second, right? We can represent the spectrum as, right? So initially, for m is equal to 0, it will be g of f multiplied with fs, right? So for m is equal to 0, it will be g of f multiplied with fs. So this will be actually what, fs into g of f, right? So this is 0, this is w, this is minus w, and then for f is equal to 1, it will be g of f multiplied by an amount fs towards right. So the different cases are possible depending upon what is fs related to w. So maybe initially I'll consider it like this, right? So this will be like this. So this will be centered at, say, fs. This will be fs plus w, this will be fs minus w, right? And for m is equal to minus 1, it will be something like this, right? So this one will be fs into g of f minus fs, and this one will be fs into g of f plus fs, so on and so forth, right? So this is how the spectrum will be. So in this case I have shown it's actually what, overlapping, right? So in this case I have shown it as overlapping, but there are three, or in fact two different cases possible, right? One case will be when fs is less than 2w, and other case can be fs greater than or equal to 2w, where w is the maximum frequency content in the original signal, right? So in this case, right, I have assumed fs minus w is less than w, right? So maybe first we'll see this case only, right? First we'll see this case only. There is actually what, replicas of g of f, like spaced at multiples of fs. You can see the adjacent replicas are overlapping in this case. This is actually called, right, aliasing, right? We'll see what actually this happens, right? This happens when, right, so this is fs minus w and this is w, right? This happens when fs minus w is less than w, or in other words, fs less than 2w, right? So when fs is less than 2w, or sampling rate is less than twice the maximum frequency content, or sampling frequency is less than twice the maximum frequency content of the original signal, right? Individual replicas of the g of f located at multiples of fs, right, adjacent replicas will overlap, right? Because of this overlap there is some issue, right? So soon I'll be discussing about the reconstruction, right? So this aliasing, because of this aliasing, reliable reconstruction won't be possible. So, right, so this overlapping is called aliasing, right? This happens when fs is less than 2w. So what is big deal about this? What if they overlap, right? So for that you should know how we'll be recovering or reconstructing the original message signal back from these samples, right? So for instance, if we consider this is actually what, an infinite sum, fs into m from minus infinity to, right? If you consider this, right, so fs into m from minus infinity to infinity at g of f minus m of s. I'm going to slightly rewrite this, right? I'll be slightly rewriting this below. So our g del of f, it is nothing but what, summation, or fs is there, fs into summation m from minus infinity to infinity g of f minus m fs, right? So I can rewrite it as, so I'll consider the case when m is equal to 0 first. So when m is equal to 0, that term will be fs into g of f, right, plus, right, and I'll consider m not equal to 0 as the second term. So m from minus infinity to infinity, as I've considered m equal to 0 here, I should mention, right, this is a summation right? The summation, the index m runs from minus infinity to infinity except for m is equal to 0, g of f minus m fs. So if you see this, you can see this g of f is the spectrum of our original signal, right? Of course it is weighted by an amount fs, right? So if you can get this back, so if, right, if you can get this back, right, this g of f alone, right, then that is the original signal. So maybe now I'll draw a case where there is no overlap, right? So this is actually what g of fs into g of f. This is centered at fs, this is at 0, and this is at, say, minus fs, and so on and so forth. Replicas will be there. So this is w, this is fs minus w, this is fs plus w, right? And again this is minus w, this is minus fs by 2, this will be plus fs by 2, this is minus fs plus w, so on and so forth, right? So in this case, right, this part is nothing but what? fs into g of f. So this, there is no overlap because I have assumed fs is greater than, right, fs is greater than 2w, right? As fs is greater than 2w, there is no overlap. So in this case, we can obtain this term alone, right, by passing this spectrum. This is actually what g del of f, right? Passing this spectrum or passing this through an ideal low pass filter having a transfer function like this, right? A transfer function like this. So as it is multiplied by fs, right, the gain of the, or the magnitude of the transfer function should be equal to what? 1 by fs, right? And it should allow from minus w to plus w. So if I should be able to reconstruct the original signal back from these samples, right, then there should not be any overlap. What if there is overlap? If there is overlap as shown in the first case, right, I cannot uh, recover the gf alone. So if I'm using a filter, right, of, say, um, which will allow from minus w to w, you can see the other part of the spectrum was actually overlapping with this, so I won't be able to reliably reconstruct. So that's why when fs is less than 2w, right, that is actually called aliasing, and we can't reconstruct the original signal back. But if fs is greater than or equal to 2w, we will be able to reconstruct back, right? So that is actually what the basic idea of sampling theorem, right? So when fs is equal to 2w, so they'll be actually what? The individual replicas of g of f located at multiples of fs will be just touching each other. There is no overlap. If fs is, so this is actually what? Fs is equal to 2w, right? If fs is greater than 2w, so then they will be what? Separated by a spectral null, right? Are separated by a long gap, right? So in this case also there is no aliasing. F is greater than 2w. So ideally the sampling theorem says, right, I'll just write it down. Sampling theorem or Nyquist sampling theorem or Nyquist criterion, right, says we can, yeah, so maybe I'll just write it down here for you people, right? A set of samples, right? I'll write it down. A set of samples can completely represent a signal, can completely represent a signal, and the original signal signal can be reliably reconstructed from the knowledge of the samples only if the sampling frequency fs is greater than or equal to twice the maximum frequency content of the original signal, right? That is, fs should be greater than or equal to 2w. So what happens is fs is less than 2w. We have seen the replicas of spectrum g of f located at the multiples of fs. The adjacent ones will overlap, and we won't be able to design a reconstruction filter to get only g of f, right? So that is called aliasing. So without aliasing, if we have to right, get back the original signal, right, the sampling frequency should be at least, right, at least twice the maximum frequency content. So the condition, right, so this fs is equal to 2w. That is actually called Nyquist rate. This is actually called Nyquist rate. So this is the minimum sampling frequency required, right? So this many number of samples should be taken in a second, so that it can completely represent an analog signal, and the analog signal can be reliably reconstructed from the known samples, right? So that is sampling theorem, right? So this is easily, right, this can be easily what understood from the spectrum of the sampled signal. So now we will discuss about reconstruction, how to reconstruct, right, reconstruction of original signal from samples, right? Reconstruction of original signals from samples, right? So this is possible only when fs is greater than or equal to 2w. If fs is less than 2w, this is not possible. So from now on, we'll be assuming, right, fs is greater than or equal to 2w, right? So what we have is, we have this g del of t, that is our sampled signal, right? It is summation n from minus infinity to infinity g of n ts del of t minus n ts, right? We do have this, and the spectrum of this will be g del of f. This is equal to, right, fs times summation n from minus infinity to infinity g of f minus n fs, right? So we can use n or f, n or m or anything, right? So I've used n here in both cases, it doesn't matter, right? So this is what we have, and we know the spectrum, right? In the case when fs is greater than 2w, it will be something like this, right? Sorry, it won't be there won't be overlapping. So the spectrum will be like this. So this is 0, this is w, this is fs minus w, this will be fs, this will be fs plus w, right? This is minus w, right? This is minus fs, and so on and so forth. And the midpoint between the gap of these two spectrum will be fs by 2. So now if I have to reconstruct, or so this will be fs into g of f, This one will be fs into g of f minus fs, right? So so on and so forth. So we are interested in this, right? Only this part. This is the original spectrum of a message signal, right? Scaled by an amount fs, right? So if I have to get back the original message signal from this, what I should do is I should pass it through a filter which has a frequency response like this, right? As this is scaled by an amount fs, so this magnitude should be 1 by fs, that is equal to ts, right? And it should at least allow from minus w to w. Maybe I'll consider actually what it will allow from minus fs by 2 to plus fs by 2. So when fs is equal to 2w, it will be actually what, from minus w to w. So for instance, I'll consider this is from minus fs by 2 to fs by 2. So anyhow, from minus fs by 2 to w, the spectral content is 0, so there is no problem if someone is writing it as minus w to w. Both are fine, right? So I'm writing it as minus fs by 2 to fs by 2, right? Where, please remember, fs is actually what, 1 by ts, that is the number of samples in a second. So this should be the transfer function of the filter, right? Or I should call transfer function of reconstruction low pass filter, right? This is an ideal low pass filter, right? So in practice we can use actually what, practical filters if fs is much beyond w, so we can have a transition, right? So we are interested in the frequency ranges from minus w to w. So even if we are having some practical filter which has a finite roll off and it spans over to above actually what fs by w, fs by 2, it won't be a problem. So this is a transfer function of an ideal reconstruction low pass filter. So I'll write h of f is equal to, right, maybe it is equal to ts for mode of f less than or equal to say w, right? Or fs by 2 I'll write, right? Mode of f less than or equal to fs by 2, and it will be 0 elsewhere, right? So this is the hff. Right now, in time domain I can assume, right? So g of del of t, right, if I am passing it through a filter of impulse response h of t, right, I'll be getting back g of t. That g of t will be nothing but what, g del of t convolved with h of t, right? Where this h of t is nothing but what, inverse Fourier transform of h of f, right? It will be nothing but inverse Fourier transform of h of f, again by means of duality property, right? We know the Fourier transform of a rectangular pulse rect of t by t is nothing but what, t sync ft, right? Just using the duality property, we can write h of t, it is nothing but what, inverse Fourier transform of h of f. You can write it as right. So you can write it as, one second, sync of fs, right? Sync of fs time t, right? So the inverse Fourier transform of this h of f is nothing but what, sync of fs times t. This fs is nothing but what, sampling rate. So we know sync of x, right? Sync of x is defined as actually what, sine pi x divided by pi x. So sync of fs times t, it's again a function in time domain, right? It's defined as, sorry, sine pi fst divided by pi fst. And if you are plotting this as a function of time, you can see, right, it will have its maxima at time instance t equal to 0, uh, right, and it will be say uh, passing through the passing through zeros at fs, 2fs, right, or yeah, uh, in those instances it will be passing through 0, right. So that will be the impulse response of the ideal reconstruction filter. So we can reconstruct g of t as sink of, right, we can reconstruct it as sink of fs times t convolved with r g del of t, right. So this is how we can reconstruct. So more details of reconstructing the signal, right, and about this sync interpolation formula we'll see in the next session. So in this session we have seen what is sampling theorem. We have seen sampling theorem. It gives us what should be the ideal sampling rate, right. So if ideal sampling rate is at least twice the maximum frequency content, the samples can completely represent the original analog signal, and from the knowledge of the samples we can reliably reconstruct the analog signal, right. So by taking the Fourier transform of our sampled signal, we have, right, verified that result, right. So that's what we have seen in today's session, and we have even seen, right, when fs is less than 2w, the individual replicas of g of f located at like multiples of fs, the adjacent ones will overlap, and that will, right, create issue while we are trying to reconstruct the original signal. That is actually called aliasing, right. And to avoid aliasing, fs should be greater than or equal to 2w, and the sampling rate fs is the limiting case that fs is equal to 2w, that is actually called the Nyquist rate of sampling. So normally, right, for ease of design of a reconstruction filter, we'll keep fs much greater compared to twice the maximum frequency content of the original signal. So that's all about what we have to discuss in today's session. In tomorrow's session, right, we'll discuss in detail about reconstruction and sync interpolation formula, and we'll try to what solve some problems, right. So thank you so much.